So when we talk about kinematics, we really talk about the motion of a particle, the movement of a particle, okay, from a particular fixed point. And we talk about straight line motion. All right, so the key attributes, if you like, of kinematics is the particle's moving in a straight line, okay, and the position is determined by its distance from the origin. All right. So if it's to the left of the origin, typically we have a negative distance. If it's to the right of the origin, we have a positive distance. All right, so the key things are displacement is the change in position. All right, so where is it at the end? However, the distance is how far we actually travel. All right, so for example, if I travel from home to school at St Bernard's, which is about 30 k's from my home, and then I travel back home again, my displacement is 0. The distance I've travelled is the 30 plus 30, which is 60 kilometres. All right, so let's have a bit of a look. A particle moves in a straight line, so its position is given by x equals that. Find its initial position. So the initial anything means t is equal to 0. So at t equal to 0, x of 0 is equal to 0 squared minus 7 times 0 plus 6, which is 6, what have we got, centimetres. So we're starting 6 centimetres to the right of the origin. At t equal to 4, my position is 4 squared minus 7 times 4 plus 6, which is 16 minus 28 plus 6, which is 22, which is negative 6 centimetres. So over that 4-second period, the distance I've travelled is more than likely the 6 centimetres where I was to the negative 6 centimetres that. So I've travelled 12 centimetres, but my displacement from the origin is 6 centimetres. Okay? Let's talk about some other terms. So there's my displacement. My velocity, or my average velocity, is the change in the displacement over the change in time. So notice that it's the change in displacement, which means where I finished to where I started over the time it's taken me to do that. The instantaneous average velocity, instantaneous velocity is dx dt, the derivative of my position. All right. So remember, the gradient is the rise over the run, and in a position time graph, the gradient is the change in position over the change in time. So that's my average. The derivative of that is the gradient of that graph, which is also the instantaneous velocity. So typically our units of velocity, metres per second, kilometres per hour, all those sorts of things. So let's go back to our question that we've been looking at. So very quickly, so my velocity is given by, I hate it when I do that. The velocity is, the rule for my velocity is given as 2t minus 7, the derivative of that equation. All right, so the initial velocity is the velocity at 0, which is negative 7 centimetres per second. So in other words, if there's my axis and I'm starting from memory out here at 6, or actually up there at 6, well then I'm heading towards, in some way, shape or form, there may not be a straight line, I'm heading back towards the origin. So the gradient there is negative, and in fact it's negative 7 centimetres, okay, at the start. When does the velocity equal 0? So velocity equal to 0, we can obviously solve that equation equal to 0. 2t minus 7 is equal to 0. 2t is equal to 7. T is equal to 7 on 2. And where am I when that happens? So at t equal to 2, x is equal to 7 on 2 squared minus 7 times 7 on 2 plus 6, which is equal to 49 on 4 minus 49 on 2 plus, let's make that on 4, 24 on 4. So that becomes negative 98 on 4, so negative 49 on 4 plus 24 on 4, negative 25 on 4. So what does that mean? That's where I am, okay, when the velocity is 0, or when my turning point occurs. Average velocity, okay, is about where I am at the start, where I am at the finish, how long has it taken me there to get there. So my position at the start, we decided was 6. My position 4 seconds later is equal to 16 minus 28 plus 6, which is negative 6. So the average velocity is equal to minus 6 over 4 minus 0, which is negative 3 centimetres per second. So that's my average velocity. My average speed, on the other hand, we really do need to sketch our graph. So we know that t squared minus 7t, so t squared minus 7t plus 6, if I factorise that, t minus 6, t minus 1. So I've got 1 and 6 are my intercepts. My turning point was at 7 on 2, which is about there, and I started at 6. So the graph looks a bit like that. All right, so now don't forget that this doesn't mean that my particle was travelling down a hill. What it means is that at 0 seconds, I was 6 centimetres in a positive direction. As it turns out, 1 second later, I've got back to the origin. And then my turning point is at the point, let me say it was 7 on 2, negative 25 on 4. Yeah? So that means after 3.5 seconds, I'm down here at negative 25 on 4 metres. And then half a second later, at t equal to 4, I was at negative 6 metres. So what I want to do now, to work out my average speed, I need the total distance I've travelled. Total distance over total time. So the time's easy. I was travelling for 4 seconds. But the distance, well, for the first 3.5 seconds, I got through that section of the curve. Okay, so, and that's a total of 6 centimetres plus another 6.25 centimetres. So that yellow length of the line, that's 12.25 centimetres. Now, in the next half a second, I travelled back to there at negative 6. So that little section there, I went from negative 6.25 to negative 6, which means I travelled 1/4 of a centimetre. So the total distance I travelled, if I add them together, is 12.5 centimetres. Yeah? So if I wanted to divide 12.5 by 4, I'm going to get 3.125 centimetres per second is my average speed. All right? So 2 really big key terms in there. If I talk about the speed, I'm talking about a total distance. if I'm talking about a velocity, I'm talking about the displacement. All right, so where I was, where I started, how long it's taken before it to happen. All right. The last of these things that we need to look at is our acceleration. And the acceleration, in the same way that the velocity is the change in distance over the change in time, my acceleration is the change in velocity over the change in time. You know, people talk about, oh, my car goes from 0 to 100 in 10 seconds. So that's talking about the acceleration of the car, all right? Again, average acceleration, what it was at the end, what it is at the start, the difference. Instantaneous acceleration is the derivative of my velocity equation. All right. Little thing, zero acceleration means the particle is moving at the constant velocity. I'm sitting on exactly 60 kilometres an hour. I'm not accelerating, I'm not decelerating, I'm just on that same speed or that same velocity. Well, that's disappointing. I've just discovered the first time I did this, the microphone was on mute. So now we'll just have a little bit of a running commentary here, lads. All right, so we've got our particle there. We need to find the initial position, velocity, acceleration. So initial means t is equal to 0. And so let's write our acceleration, our position as x. So if I put 0 in for t, clearly I get the x is equal to 5. For velocity, that's dx dt. Sometimes we write it as x dot or x dash of t. And so if we differentiate that, we're going to have 3t squared minus 12t plus, well, that's it, isn't it? Initial, again, means t is equal to 0. So clearly if I put t equal to 0, my velocity is also going to be 0. All right, and then we make our way to acceleration. Acceleration is the rate of change of velocity, so dv dt. dv dt is 6t minus 12. And again, if I put t equal to 0, my acceleration is going to be negative 12 meters per second squared. So the negative just simply means we're moving in the left direction. So if the positive axis right on the number line is positive, left is negative. All right, so now we need to find the times when the particle is at rest. So when is a particle not moving? It's when the velocity is 0. So I need a rule for my velocity, which I've got there at 3t squared minus 12t. And I've got to solve that equal to 0. So if I factorise, take 3t out, 3t, and I get t minus 4 in brackets equal to 0. So solving equal to 0 will give me t equal to 0 and t equal to 4. So my velocity is 0 at those times, which we sort of knew one of them from the first question. So now we also need to know its position and its acceleration. So we now got to find the appropriate equation. So what are we going to do first? Excuse me. Okay, so we can see there at t equal to 4, my position, x of 4, substitute 4 in, is 4 cubed minus 6 times 4 squared plus 5, which will give me 64 minus 16 by 6, so 96 plus 5. 69 minus 26 is negative 27. So we're 27 meters to the left of the origin. Okay. Acceleration, exactly the same process. Get our rule for the acceleration, substitute 4 in. Which will give me what? 6 by 4 is 24 minus 12 is 12 meters per second. We need to do the same thing at t equal to 0. Well, at t equal to 0, we already know the position. It was at 5. And we know the acceleration, so we probably don't need to rewrite those things. Or we should rewrite them for the question, but we don't have to recalculate them. That should hopefully take us to example 19. So again, we've got a car starting from rest. It moves a certain distance S meters in t seconds. So really the only difference is instead of having x equals, I've got s equals. So S is 1/6 of t cubed plus 1/4 of t squared. So initial acceleration and the acceleration at t equal to 2. So my acceleration, I need first my velocity, which will give me 3 by 1 on 6t squared plus 2 on 4t. And then my acceleration is the dv dt, the rate of change of velocity, which will give me 6 on 6t plus a half. Now, if I just substitute my time values in, initial implies t equal to 0. So initially, my particle is accelerating 1/2 meter per second in a positive direction. And obviously then at t equal to 2, substitute that in. 2 by 1 is 2. Oh, sorry. No, I've written t equal to 4. That should be t equal to 2, shouldn't it? Ignore that. Ignore that, fellas. So t equal to 4, the acceleration is 4.5, but we should have had a t equal to 2, which would have been 2.5. Anyway, small error. You'll live. Example 20. So hopefully you're getting a feel for it now. We've got a position rule, t cubed minus 6t squared plus 9t. Find at what times and in what positions the point will have zero velocity. Zero velocity, dx dt is equal to 0. V is equal to the derivative, 3t squared minus 12t plus 9. We want to solve it equal to 0, so we've got to factorise. 3 is a common factor, so let's take that out first. And then we can see that we'll end up with t minus 3, t minus 1. So we've got to be reasonable with our quadratic factorising, gents. Solve that, we get t equal to 1 and t equal to 3. So that's when the particle has got a 0 velocity. I need to also find where, at what position. So if I substitute t equal to 1 and t equal to 3 into my position equation, we can work that out. So if x is equal to 3, we get 3 cubed minus 6 times 3 squared plus 9 times 3. 3 cubed is 27. 3 squared is 9. 6 9 is 54 plus 27. 27 plus 27 minus 54 is 0. So we're back to the origin after 3 seconds. T equal to 1, substituted in. 1 cubed minus 6 plus 9. What's that? 10 minus 6, which is 4. So we're 4 meters in a positive direction. Find the acceleration at those instances. Probably should be instances, I reckon. T equal to 1, t equal to 3. I need a rule for acceleration. Acceleration is dv dt. And that's going to be equal to the derivative, 6t minus 12. So there's a rule for my acceleration. If we put, what are we going to put in first? If I put t equal to 1 in first, I'm going to end up with 6 minus 12, which is negative 6 meters per second squared. And then if I put t equal to 3 in, I'm going to get 6 3s are 18 minus 12. And we'll end up with positive 6 meters per second squared. All right, so just don't forget that the negative sign gives you the direction that we're heading in. All right. Finally, find its velocity when the acceleration is 0. So I've just, hopefully you can see now, it's just a case of picking the right equation. As soon as we got one equation, really we've got 3. We've got a rule for acceleration, velocity, and position. I need acceleration equal to 0, so 6t minus 12 equal to 0, so t is equal to 2. Pop that into the velocity equation, which is equal to 3 times 2 squared minus 12 times 2 plus 9. 2 squared is 4 by 3, which is 12, minus 24 plus 9, so 21 minus 24 is negative 3 meters per second. So we're travelling 3 meters per second to the left. Job done.